Let's start to define some terms so that you can understand this subject about radioactive decay and the basis for radioactive dating. Every element, whether it's carbon, oxygen, hydrogen, is made up of atoms, and each of these atoms has the same unique number of electrons and protons. And the number of neutrons, however, in the nucleus of the atoms in many elements can vary. So, for example, you've got carbon-12, carbon-13 and carbon-14. The differences in those is that there are more neutrons, 2 more neutrons in carbon-14 than in carbon-12. Now, these 3 different types of carbon atoms are called isotopes. Now, some atoms in some elements have too many neutrons in their nuclei, so they become unstable. They can't hang on to them. There's not enough energy to hold all the particles together. And so some of these unstable isotopes may decay by spitting out some of the particles that are held in the nucleus, okay? And so that to reduce their size to become more stable. But when they do that, the number of particles in the nucleus has changed, so they become a different element, because each element is defined by the numbers of protons in the nucleus. So this process where the unstable atoms decay or spit out particles is called radioactive decay, because people used to use a Geiger counter or something like that to hear the clicks of the particles that were coming off, for example, off uranium. And these decaying isotopes are known as radioactive isotopes, or just radioisotopes for short. And when these radioisotopes decay, they result, the end product are stable isotopes of different elements. Okay, so you go from a parent element to a daughter element. The decaying isotopes are called parent, and the resultant stable isotopes are called daughters. Okay, the parent decays and changes to a new element, which is a daughter element. It's not that difficult, you just got the terminology to get your brain around. And so there's ones of interest to us tonight that are of interest to geologists and archaeologists. Everyone's familiar with carbon-14, which decays to nitrogen-14, and we'll talk about that more a little later on tonight. But people have heard of uranium that decays to lead, potassium that decays to argon. You might not have heard about rubidium that decays to strontium, but you've also got samarium, which is a rare earth element that decays to neodymium. And those numbers, like uranium-238, the 238 describes the size of the nucleus of that atom. And it's large, it's the common uranium atom, and it decays down to lead-206. And you're going to hear a lot about that in the next few days. So minerals, rocks and fossils can all contain some of these parent radioisotopes and daughter isotopes, which is the basis for being able to do this radioactive dating. Well, how does it work? A rock is chemically tested for these isotopes. You get samples, you take them to a laboratory, and they measure the amounts of these isotopes. And it is assumed that if the rate of radioactive decay has remained constant at the rate we measure today in the laboratory, then you can calculate how long it has taken for the measured amount of daughter to accumulate, and that's the rock's age. Now, I've included on the screen there a little hourglass to give you the idea, because the analogy is quite simple. The sand in the top glass bowl represents the parent atoms. The sand in the bottom glass bowl represents the daughter atoms. As they fall, the parent atoms change to daughter atoms down the bottom, and the falling process is analogous to radioactive decay. Now, you can understand that if you take an hourglass like that and say it represents 1 hour's worth of sand, if you start with all the sand in the top glass bowl, within an hour it will all have fallen to the bottom. Okay? So it's quite simple. You start by turning all the glass over, so you've got all the sand in the top glass bowl at the beginning of your timing experiment. You leave it running and you go out and start doing the laundry or cooking a meal, and you come back, you want to know how long you've been doing that task, and you notice that half the sand is up the top and half the sand is down the bottom. So how long has it taken you to do that job? Half an hour, because you know the decay rate is 1 hour. And you've still got half left at the bottom, at the top, and half left at the bottom. Half at the top and half at the bottom. So it's not that difficult. That's what the geologists do. They measure the amounts. Knowing the rate, they can calculate how long ago the process started. And this process is supposed to have started when the rock formed, so that becomes the age of the rock. It really isn't that difficult to understand. However, here's the catch. You have to make assumptions. You have to make assumptions. Because the method only works if you assume these three things are true. First of all, that assumption number one, the amounts of parent and daughter isotopes at the beginning when the rock formed must be known. In other words, the initial conditions. Now, when you started the hourglass, you tipped it up, you had everything at the top, and then you went off and did your job. But the geologists weren't there when the rocks formed. So how do they know that there were only uranium atoms and no lead atoms? What if there were lead atoms there to begin with when the rock was formed? Unless you know the initial conditions, you don't know whether your clock really started ticking with only uranium atoms. So you have to assume that the initial conditions, even though you weren't there. Secondly, you have to assume that all the daughter atoms that you measure in the rock today have only been derived by radioactive decay in that rock from the parent atoms. In other words, it has to be a closed system. In other words, you can't have contamination. What if in the supposed millions of years, groundwater flowing through the rock added lead or washed away uranium? You'd never know for sure whether your rock has remained uncontaminated for millions and millions and millions of years. Now, you can understand it's a wide sweeping assumption. I mean, it's like with your hourglass. Little did you know while you were out doing the laundry, your mischievous 13-year-old came and lifted up the lid and put some more sand in. He contaminated your clock. And you thought you had been going for half an hour, but actually you've been going for 40 minutes. You see what happens? If it isn't a closed system that can't be contaminated, you can't use that clock accurately. And thirdly, obviously, you have to know the rate of radioactive decay. It must have always been constant at today's measured rate. Now, the scientists have only been measuring radioactive decay for the last 100 or so years. It was only discovered just over 100 years ago. And so they've taken 100 years of measurements and assumed that those decay rates have been constant for millions and millions and billions of years. Now, that's an enormous extrapolation of 5 orders of magnitude. So none of these assumptions are actually provable because you weren't there to test the rocks in the past. The past is no longer gone. It's gone. We can't observe and measure the past or test it. So these assumptions are not even reasonable. In everyday experience, they're not even reasonable. The daughter atoms may be inherited when the rock forms. For example, in volcanic gases, you can get extra argon. Subsequent contamination is common. Now, I want you to understand that I'm not questioning the quality of the chemical analyses. If you ever visit a university laboratory where they do these measurements, the equipment is worth millions of dollars. And the sophistication is incredible. In the case of radiocarbon, they can actually count individual atoms. And they can reproduce their measurements with incredible precision. So we don't dispute the quality of the chemical analyses. But what happens is the geologist takes the analyses and interprets the numbers to calculate an age based on these assumptions. So what we're disputing is the ages and the assumptions. The need for assumption number one, however, the initial conditions, geologists have found a way to get around that by using the so-called isochron method, which we don't have time to go into details tonight because it's fairly complex. Assumption number two is easily discovered to be violated when contamination is detected. It's quite common to find rocks that are contaminated when they do the analyses, and so they discard those results. Not all results are ever published if they don't fit preconceived ideas about what the age of the rock should be. They put it down to contamination. However, it is insisted that assumption number three, that is a constant decay rate, is universally true. It's supposed to be a universal condition, just like the speed of light, that they say can't be violated. Why? Because the resultant millions of years, ages, are needed for evolution to be possible, as we discussed this morning. You see, however, we're all aware that these millions of years, ages, are certainly way out of sync with the biblical timescale of only 6,000 years. So something is radically wrong if these radioactive methods give millions and billions of years when the Bible only talks about 6,000 years. But the interesting thing that I want to point out tonight, and I'll come back to this later, is often the resultant millions of years ages usually still match the relative order of the strata. In other words, rock layers down the bottom usually give older ages than rock layers up the top. And there's a reason for it, as we'll see shortly. But just hold that thought and we'll come back to it. For example, Precambrian rocks, ones down in the crystalline basement of the Grand Canyon that we'll talk about on Thursday night, usually date at older than 545 million years. And that's supposed to be the age of the Precambrian. So the question we should ask ourselves, if there's a matching of the relative order with the millions of years ages, which are highly inflated, of course, compared to the biblical timescale, we have to ask ourselves, why should radioactive decay rates have always been constant at today's measured rates? Why should that be an assumed constant? What if radioactive decay had changed in the past? If it had, and the clocks tick faster, then we couldn't use them to measure the ages of rocks. Well, I was involved in an 8-year project initiated by creationists called the Radioisotopes and Age of the Earth Project, the RATE project. And that project concluded that assumption number 3, that is, the constant decay rate assumption, is absolutely false. And I want to demonstrate that to you tonight. In this project, we discovered 5 independent lines of evidence that demonstrate that radioactive decays must have been grossly accelerated during one or more recent catastrophic geological events, especially during Noah's flood. Now, that makes sense. If we had catastrophic rock formation and other geological processes during the flood, why not catastrophic rates of radioactive decay? So if that's the case, and the clocks tick faster in the past, radioactive dating cannot be used to accurately give us the absolute millions of years ages that are claimed for the rocks. Well, let's look at these evidences. Number 1, helium in zircons. Zirconium silicate is a little mineral called zircon, and in zircon, these zircon grains, they contain uranium. They're highly radioactive. And as a result of having the uranium. And as the uranium decays, a byproduct of that decay is helium. So every atom, uranium atom that decays actually produces 8 helium atoms as a byproduct. Now, some years ago, there were investigations into potential geothermal energy in the Los Alamos area of New Mexico. And in this drill hole, they intersected a granite. And in the granite, we find these zircon little crystals, microscopic crystals that can be separated from the rock, as you can see in that photograph there. Now, the age of these zircon crystals, based on uranium decaying to lead, was 1.5 billion years. 1.5 billion years. However, something interesting. As you go down the drill hole, you can see in this table, at deeper depths, the in-situ temperature rose. That's right. At nearly 4 kilometres down, the rock was at 277 degrees. That's more than twice the boiling point of water. That's how hot the rocks were at that depth. And in that last column, you see that helium percent. Okay? That number represents the percentage of the 1.5 billion years worth of helium that was still in those zircon crystals. At only 750 metres, the 1.5 billion years worth of helium, 20% of it had been lost and 80% had been retained in these crystals. You might say, so what? Well, it's very significant, as this research discovered. Why? Because helium leaks out of these crystals. It's only a tiny atom. It's the second smallest atom. You've got hydrogen and then helium. And you've got this crystalline structure of the atoms in a pattern like you see in the diagram there. And the helium atoms can slip out their way between the zirconium and silicon and oxygen atoms. And the hotter the crystal makes sense. It makes sense that the faster the helium leaks out. Why? You heat the crystal, the atoms vibrate more dramatically, so the helium atoms get more energy and they slip out more easily. And of course that makes sense. In that last table, the deeper you went in the hole, the hotter the temperature, the less helium that was still left. Now, based on this, an experiment was proposed. We know that the hotter the zircons, the faster the leakage rate, as you can see in that graph. Now, don't get fazed by these diagrams and graphs. They're really simple to understand. And we can make a calculation. The helium lost divided by the time is what we call the leakage rate. And so we wanted to look at this data in this drill hole to see if you plugged in 6,000 years, what would the leakage rate be? You'd have lost a lot of it very quickly. It'd have to leak out very quickly in 6,000 years. Whereas if these rocks were really 1.5 billion years old, to still have 80% of the helium in some of those zircon crystals meant that the leakage would have to be very slow. Okay? So we set up an experiment because, you see, no one had before measured how quickly helium leaks out. And so we published this prediction on this graph, which is temperature versus leakage rate. Diffusivity is just a fancy term for leakage. Okay? You can see that from that table I showed you before of the different depths and different temperatures, you can see the top one there is the 6,000 year line. That's how fast the leakage would have to be if all that helium leaked out in only 6,000 years. But if it leaked out in 1.5 billion years, it would be a lot slower, so that's further down in the graph. And the factor of difference is 100,000, okay? Now, we published this prediction in the year 2000, and then we did the experiments. Now, we were laying our necks on the line because we could be proved wrong just like that. What happened when the results came in? Bingo. the data matched exactly, not even slightly off, exactly to the 6,000-year line. And so it was done in a world-class laboratory, actually at Caltech. And the experimental data verified the 6,000-year prediction and totally annihilated the 1.5 billion-year prediction. Isn't that incredible? And when you take the individual samples with the amount of helium left and do a calculation of the age from the leakage rate, the average was around 6,000 years. And so that means, what does that mean? It means that these two clocks were ticking at different rates. The helium leakage clock, we know what leakage is all about. We can study it from well-known scientific laws, whereas people don't fully understand how radioactive decay occurs. That means the only way these two clocks could be reconciled is, in a sense, a real sense, that 1.5 billion years of the nuclear decay occurred during 6,000 years of helium diffusion. Since helium diffusion is a known measurable property that we can understand the physics of it, that means the radioactive decay clock had to have been speeded up by 100,000 times. And that, we believe, occurred during the flood. And that makes sense of catastrophic geological processes during the flood. But as my colleague just said, there's more. Evidence number 2, different radioisotope ages. Well, the 4 major radioisotope dating methods used on rocks are potassium to argon, rubidium to strontium, uranium to lead, samarium to neodymium. Now, when most geologists do their studies, they only ever use 1 or 2 of these methods on their rock samples. Why? Because they say, well, whatever clock we use, we should get the same results. Whether we use the uranium method or the potassium method, it doesn't matter. Because the rock only has one age, and these clocks are all supposed to agree with one another. Therefore, they should all use the same ages. And so they only ever do 1 or more dating methods on the same rock samples. And if someone ever wants to repeat the work, they usually collect different samples to use a different method. So we said, okay, we'll get smart. We'll use all 4 methods on the same rock samples to really see whether these clocks agree with one another. And we also use the superior isochron method that I talked about earlier. Why is it superior? Because instead of using 1 sample, you use 5 or more samples. And in many of our studies, we used up to 20 samples so that nobody could accuse us of being lied on with data. And that's very important. The more data, the more ability to get tighter statistics in our results. And that's exactly what we found. So I want to show you 4 rock units from the Grand Canyon. First of all, there's this rock unit where the molten rock was squeezed like toothpaste between sedimentary rocks. It's called a sill. And the rock is a diabase, which is like a basalt. And these are the results that we obtained. The potassium-argon result was 841.5 million years. The rubidium-strontium, 1,060 million years. The uranium-lead was 1,250 million years. And the samarium-neodymium, 1,379 million years. Do any of those agree with one another? Maybe there's an option E, none of the above. And interestingly, with some of these results, we actually took a single sample and separated it into its constituent minerals and analysed the individual minerals. So you would think the individual minerals together in the same rock should always give the same age with all the different methods, but they didn't. There's more. This is a series of basalt lava flows deep in the Grand Canyon, in the eastern Grand Canyon. Here's the results. Potassium-argon, 516 million years. Rubidium-strontium, double that at 1.1 billion years, or 1,111 million years. And samarium-neodymium, 3 times the potassium-argon at 1,588 million years. That's not very good hitting the bullseye, is it? The samarium is 3 times the size of the potassium-argon result. Not very good. We go to another rock unit, got a strange name, amphibolite. It's actually a metamorphosed basalt, ancient lava flows that were heated up and changed. Their mineral composition changed. And guess what? Rubidium, strontium gave an age of 1,240 million years. Uranium, lead, or lead gave 1,883 million years, and samarium, neodymium, 1,655 million years. Now, you don't have to know all the technicalities to see that those numbers are not the same. They're not even close. And then there's a granite, the Earl's Chasm granodiorite, a type of granite in the Grand Canyon. And the rubidium, strontium gauge an age of 1,512 million years, the lead, 1,933 million years, samarium, neodymium, 1,664 million years. Again, a great variance in these results. Now, there were some interesting patterns. We need to understand that these multiple radioisotopes from these 4 rock units always disagreed, always. And yet each of these rock units represent a single unique geologic event, the formation of this sill, or the metamorphosis of those lavas, the eruption of volcanic lavas, or the crystallisation of a granite. A unique one-time geologic event. So it should have had the same age with these clocks, but they weren't the same. So if these radioactive clocks were accurate, always ticking at the same rates that we measured today, each clock should have given the same age, but they didn't. Therefore, the conclusion we come to is that each radioactive clock must have ticked at different and faster rates than today to give the different ages. Let me illustrate what I mean. For example, that Cardenas basalt, while the potassium-argon clock ticked through 516 million years, the rubidium-strontium clock was ticking more rapidly through 1,111 million years, and the samarium-neodymium clock was going even faster and faster, ticking through 1,588 million years. Now, I'm using the millions of years only in the sense that that's the numbers that come out of the equations. I'm not saying they're real millions of years. All I'm saying is that's relative to one another. The older age means the clock had to go faster and faster than the younger age for the 2 clocks to be reconciled. Was there a pattern? Yes, there was. Is there a factor, the underlying factor that we can determine? Yes, because if there's a pattern in these results, and there are patterns, that means there's a systematic process going on that would explain this accelerated nuclear decay. So if we look at some of these results, you've got the diabase sill, and notice that the potassium is younger than the rubidium, the same in the Cardenas basalt. The potassium is younger than the rubidium. The potassium has a shorter half-life, it decays more rapidly and it gave a younger age. The rubidium-strontium, which decays by the same beta decay process, gives an older age. That's interesting. And notice, rubidium-strontium decay by the beta process, which I don't have time to explain, and uranium and samarium decay by the alpha process, and the alpha process always gives older ages than the beta process. Now you see, if this was a random thing happening, you wouldn't have those patterns. We see the same in these other 2 rock units. The rubidium is always less than the uranium, the beta is always less than the alpha, the uranium and samarium. And that's what we found. The uranium and samarium neodymium ages, the alpha ages, are always older than the potassium argon and rubidium strontium beta decay ages. And sometimes the longer the present half-lives, that's the greater, the slower the decay rate, the older were the ages. So rubidium, which had a slower decay rate, was always older than potassium, which has a faster decay rate. And we can also look at the atomic weight. And again, we find that the heavier atoms always give older ages than the lighter atoms. And therefore, there's a relationship to these ages between the decay rate and the size of the atom and the type of decay. We concluded that it has to do with the binding energy of the or nuclear forces that hold the nuclei together. That you only have to make and theoretically you can show you only have to make a small change and you will accelerate nuclear decay. And I don't have time to go into that tonight. When all four major methods were used to date the same samples from the same rocks, they invariably yielded different ages. And these different ages can be explained if these radioactive clocks ticked at faster rates in the past, at different faster rates than today's measured slow rates. And so we have to conclude that these different radioisotope ages from the same rocks are evidence of accelerated nuclear decay, matching what we discovered from the helium leaking out of those zircon crystals. Evidence number 3, abundant fission tracks. Now, what on earth are these? Well, let me explain. Again, let's go to the bottom of the Grand Canyon, and one of the limestones down the bottom of the Grand Canyon, inside it, there's a little volcanic ash bed from a volcanic eruption. And inside this volcanic ash bed, which as you can see there where the pen is for scale, it's only about 2 to 3 inches thick. This volcanic ash bed contains zircon crystals, these zirconium silicate crystals that contain uranium atoms. Now, sometimes a uranium atom, instead of decaying, well, as I said, it's unstable and it decays by radioactive decay, okay? And what it does is it ejects just a couple of little particles and the nucleus just gets a little bit smaller. But on other occasions, we have what is known as fission. That is, instead of a little bit of the atom of the nucleus coming off, the nucleus splits in half. This is the basis of the atomic bomb. It's called nuclear fission. The atom itself splits in half. So you get 2 fragments or 2 new atoms of similar size rather than something very large, still similar to the size of a uranium atom. So what happens? As the atom splits, the 2 halves fly apart, the 2 small atoms, and this process is called fission. Fission is division. Okay, so what happens? The atom splits apart and it breaks into 2 new atoms. What happens therefore inside a zircon crystal is that those 2 atoms flying apart damage the crystal and form a visible damage trail or track, which is called a fission track. And you can actually study these under a microscope. Here's some photographs. You can actually see where the atoms have split apart and damaged the zircon crystals. Now, the more atoms that have split apart, the more of these tracks are produced. So if you know the rate at which this fission or fission process occurs, you can count the number of tracks and use it as an age calculating method. And so this is something you can physically observe. In other words, nuclear decay has occurred through geologic time. There's no question about it. We have physical evidence that there has been abundant nuclear decay. Well, we again look at 3 examples. In the Peach Springs volcanic rock unit near Kingman, Arizona, we find fission tracks equivalent to 21 million years worth of nuclear decay at today's rate of fission. This is at the top of the flood sequence. We go down a little further, we go to the Morrison Formation, which is famous for its dinosaurs in Utah. Again, we find a volcanic ash bed, we extract the zircons, and we find there are fission tracks equal to 136 million years worth of nuclear decay at today's measured rate. Okay, I'm not saying there was 136 million years, I'm just saying if you use the assumption of today's measured rate and extrapolate back, that's the number you get. And again, if we go to the bottom of the Grand Canyon, the lowest of the units in the walls of the Grand Canyon, the Tapeats sandstone, that we mentioned last night, it also has a volcanic ash bed in it, and the zircon crystals there have fission tracks equivalent to up to 500 million years worth of decay at today's measured rate. And that's at the bottom of the flood sequence. Now that makes sense. We know that therefore there's abundant evidence of nuclear decay during the time these rock layers were formed. in the Grand Canyon, Colorado region, up to 500 million years worth. And it matches the supposed ages of these rocks. In other words, they're in the right relative order. But we know from our biblical foundations, our biblical time frame, that all of this occurred during the year of the flood. Therefore, we have observable physical evidence of 500 million years worth, measured at today's rates, of nuclear decay during the 1 year flood. In other words, the decay rate had to be grossly accelerated during the flood. And we have the observable physical evidence that that occurred. Evidence number 4. Uranium and polonium radiohalos. Now, this is highly complex, and we're going to have a whole session on it on Thursday night. So if you haven't understood this time around, come back on Thursday night. But it's not that difficult to understand. Again, we go to a granite, say in Southern California, east of San Diego. Most granites contain a flaky black mineral called biotite. It's a mica mineral. You can peel the flakes apart. There's a white mica and there's a black mica. The black one is called biotite. And inside these biotite crystals we find zircons. Again, this interesting crystal called zirconium silicate. It's interesting because it has uranium atoms in it, okay? But these radioactive uranium atoms are spitting out these alpha particles, which is the name of there's 2 neutrons and 2 protons that the nucleus spits out to reduce its size to become more stable. And we call the 2 protons and the 2 neutrons together an alpha particle. That's alpha decay. Okay, but once that's happened once, the parent uranium atom has become another daughter atom, but that's still unstable. It decays again. In fact, to get down to lead, there are actually 8 steps where these alpha particles are spat out like little bullets from the uranium atom to make it more and more stable till it eventually gets down to lead. And so you have here a radioactive uranium atom. It spits out an alpha particle, becomes a daughter atom, spits out another alpha particle, and does it 8 times altogether before it gets to the lead atom. Now, why is this significant? Well, let's go further. When the zircon crystals are large, as in the first example I gave you from that drill hole in Los Alamos where we got the helium studies, where the zircon crystals are long enough, are big enough, the alpha particles can't escape. They don't have enough energy to escape from the zircon crystals. They pick up stray electrons and become helium atoms, which is why we had helium in those zircon crystals. But when the zircon crystals are tiny, the alpha particles escape and they shoot out like little bullets into the surrounding biotite crystal. And it's like firing a gun at a plasterboard wall. You leave a hole in it. So these alpha particles are so energetic that they damage the surrounding crystal, and it damages it and discolours it. And so you can see here an example of, in the centre you can see a tiny little zircon crystal, and you can see the discoloration around that zircon crystal because of all these little bullets, radioactive bullets coming out. It's like when they used to use radioactive decay. You put a piece of uranium on a photographic plate, it would leave a darkened area. Well, it's similar in a biotite crystal. And these are called radioactive halos, or radiohalos for short. And they are evidence, they're physical evidence of abundant radioactive decay. Now, interestingly, each of these steps, and I said there are 8 steps from uranium down to lead, every one of those steps produces alpha particles or bullets of different energies. What does that mean? It's like having a handgun versus a rifle. The rifle's got to shoot the bullet further than the handgun. And so these alpha particles go different distances, and so the sphere of discoloration is at different distances according to what element in that decay chain shot out those little bullets. And you can see in this diagram the list of parent atoms that shoot out the alpha particles from uranium all the way down to lead and the different energies. And where the bullets stop, they produce the most damage, which produces a darkened ring. So, a fully formed uranium radiohalo has 8 rings, as you can see in that photograph. And it has been determined that to form this discoloration at such an intensity that it can be observed under a microscope requires 500 million to 1 billion of these alpha particles. Now, that much decay is equivalent to at least 100 million years worth of radioactive decay measured at today's rates. So when you see these radiohalos in a granite, it means that that granite has suffered at least 100 million years of radioactive decay. That's at today's rate. I'm not saying the million years ever happened. All I'm saying is if you take the measured rate today and extrapolate it back, that's the number you get. Now, granites all around the world contain these dark uranium radiohalos, and I've had samples now from 4 or 5 continents. And everywhere I look, I find these radiohalos. And so we go to Arizona in the Grand Canyon area. We go to southern Australia. We can go to southeastern Australia. We can look in England, the Lake District of England. We can go to the Confederate Memorial outside of Georgia and find these radiohalos. Don't tell them I got samples from there, will you? And also you can go to Yosemite National Park and find halos in rocks like the Half Dome granite. So, granites all around the world contain this abundant physical evidence of nuclear decay, at least 100 million years worth. And interestingly, you need to remember that many of these granites intrude into fossil-bearing sedimentary rocks. One of those granites in southeastern Australia, you can actually walk from the fossil-bearing rocks, sedimentary rocks, through where the heat of the granite has metamorphosed the rocks and then into the granite. So we know that the granite formed after the sedimentary rocks formed with fossils in them. So when did the fossiliferous sedimentary rocks form? During the flood. That means 100 million years at least worth of radioactive decay in these granites had to occur during the flood. It's not that difficult to understand, is it? Now, in many granites, there are also single ring halos that are very small, sitting alongside the larger uranium radiohalos. And the larger one there's so much radioactivity that it's blurred all the rings. You can't see them all. So there's hundreds of millions of years worth of decay in that photograph. And in this one too. In some granites, in biotite flakes, we find 2 rings. The 2-ring one, that's very hard to see the outer ring, but it's there. It's there. And in some granites, you actually find 3-ringed halos. What does this mean? This is different to the 8-ring uranium radiohalos. Well, interestingly, these rings match the last 3 elements in that decay chain, well, the last 3 isotopes. It's all the same element. It's an element called polonium, discovered by Marie Curie and named after a homeland of Poland. It's a rare metal. And there's 3 isotopes in the decay chain of uranium, 218, 214 and 210. And so we find that these elements are responsible, this element, polonium, is responsible for forming these 1, 2 and 3-ring polonium, these radiohalos. And these polonium radiohalos are found in many granites around the world, alongside uranium radiohalos in Arizona, in South Australia, again in the Lake District of England. These are just a few examples. East of San Diego. But here's the problem. These polonium radiohalos have been described in a famous US court case as a very tiny mystery. It was the 1989 Arkansas trial. And on the witness stand was the Deputy Director of the US Geological Survey. And when he was confronted with this evidence, he scratched his head and said, it's just a mystery. Didn't have an answer. Why? Where did the polonium come from to produce these radiohalos? It's not in the biotite. The actual closest source is the uranium in the zircons, because remember, the uranium is decaying down to polonium as it's producing the radiohalo, the uranium radiohalo. That means the polonium had to be scavenged from the zircon crystals as the uranium was decaying and transported to produce independent polonium radiohalos. That means the uranium and polonium radiohalos had to form at the same time. And here's the crux of the matter. The uranium must deliver enough polonium to generate 500 million to 1 billion alpha particles for each dark polonium radiohalo before the polonium decays. Okay, but what's the rate of decay of these polonium isotopes? Polonium-218 is 3.1 minutes. Polonium-214 is 164 microseconds. You blink and it's gone. And polonium-210 was 138 days. In other words, at least 100 million years worth of uranium decay had to occur while you blinked during the flood. So this is evidence, physical evidence, that not only that abundant nuclear decay has occurred during the flood, but there has been abundant nuclear decay. Millions, hundreds of millions of years of nuclear decay occurred within the single year of the flood. And you see what I mean? We've now got 4 independent lines of evidence that decay rates were accelerated during the flood. Well, there's more. You've been waiting for this all night, haven't you? Radiocarbon. Everybody knows about radiocarbon, and we find it in fossils. You mightn't believe it, but we do. The scientific community has recognised this for many years, and they've never looked at the implications. Radiocarbon is different from the other elements I've talked about. Why? Well, it's formed differently. Cosmic rays in the upper atmosphere produce fast-moving neutrons that collide with nitrogen-14 that produces carbon-14 in the upper atmosphere, which combines with oxygen to produce carbon dioxide. It's in the air you breathe, and you're all tonight a threat to public health and safety because you're all radioactive with radiocarbon. It was in the food that you ate tonight for dinner, and we should put out a sign out there that this actually should be a nuclear-free zone, and we wouldn't let you in because you're all radioactive with radiocarbon. Now, think about it. As your body then, you go on living, the carbon-14 that you took into your body decays away and returns to nitrogen-14. And as long as you eat more food, you're going to get more radiocarbon, aren't you, to replace that which is decaying away. But your great-great-great-grandmother, when she died, she stopped eating. So since her bones have been in the cemetery, she's got less and less radiocarbon in her bones, so it's kept on decaying back to nitrogen-14. So it's quite simple. If you want to know how long, whether the tombstone is correct in when she died, you measure how much radiocarbon is in her bones and compare it to the amount of radiocarbon in your bones. And the difference, you know how quickly radiocarbon decays, you can calculate how long ago she died. That's how the method works. It's really quite simple. But here's the interesting sidelight to this story. As I said before, the equipment that is used today is so powerful that you can actually count individual radiocarbon atoms, carbon-14 atoms. However, the detection limit is as good as 0.001% of the present level of carbon-14, which is equivalent to 95,000 years. That's right, you can only go back, theoretically, you can only go back 95,000 years with radiocarbon. You don't date fossils at millions of years with radiocarbon. The reason is that radiocarbon has a half-life of 5,730 years. And it means that any ancient organic carbon conventionally older than 95,000 years, like dinosaur bones, should contain no detectable radiocarbon. Let me put it another way. If every atom in the Earth was radiocarbon, within 1 million years it all have decayed away. There'd be none left. So that's why the scientists never used radiocarbon to date fossils at millions of years. But here's the embarrassment. Even in the secular literature, yes, it's already published in the journal Radiocarbon and one other secular journal, you actually find dates, radiocarbon measurements on fossils that are supposedly up to 500 million years old, and they all have radiocarbon in them. Why did they never tell us that in their textbooks? In fact, they're all young. They're not 500 million years old. So you see, I was mischievous a little while ago, and I decided I'd collect some samples and send them to a radiocarbon lab. But I didn't tell them how old the sample was, so I sent them a piece of fossilised wood from a 189 million year old rock in England. And guess what? It returned a radiocarbon age of only 24,000 years. I took a piece of coal from Australia that was 250 million years old supposedly. It gave an age of 33,700 years. And I went up to Northern California and collected samples of ammonite shells with fossil wood next to them. Okay? And these are supposed to be 112 to 120 million years old. And look at the radiocarbon. The wood and the shell almost matched one another. I had 4 samples like this, and some of them were almost exactly the same, in two different materials. So what we did in this RATE project, we decided to take coal samples from different parts of the United States that are stored at Penn State University by the US Department of Energy. And here's the samples. 3 of the samples were from coals that are supposed to be 34 to 55 million years old. 3 of the samples were from coal beds that are supposed to be 65 to 145 million years old. And 4 of them were from coal beds that are supposed to be 299 to 318 million years old. And you can see they've come from a wide distribution around the United States. And guess what? They all had radiocarbon in them. In fact, they all had about the same amount of radiocarbon in them. They were all about the same radiocarbon age. Surprise, surprise. Where did all these coal beds form? Right, during the flood. They all formed in 1 year. All these trees lived just before the flood. Would you expect to give you the same radiocarbon age? Absolutely. Whether they were supposedly 300 million years old or 40 million years old, they gave the same radiocarbon age. Isn't it great to be a creationist, as my good friend John Morris used to say? Well, we went further. We also took diamonds that are made up of carbon to see if the diamonds would have radiocarbon in them. These are conventionally dated at 1 to 3 billion years old. And yet all these diamond samples contained measurable radiocarbon regardless of whether they were 1 to 3 billion years old. So, we found similar amounts of measurable radiocarbon in coal samples regardless of their conventional age. These represented, of course, pre-flood plants buried during the flood, all at the same time. So it wasn't surprising to find that they all gave the same radiocarbon age. Yes, it was inflated, and I'll explain why in a moment, but they all gave the same radiocarbon age. And the same with the deep earth diamonds. These diamonds come from 200 miles down inside the earth. Most people don't realise they come from 200 miles down inside the earth by explosive volcanic action in just about 2 hours. And yet they had radiocarbon in them regardless of their claimed billions of years ages. And with a diamond, this can't be contamination because diamond is the hardest substance known and it's impervious to contamination. So this has to be radiocarbon that is in situ to the diamonds when they formed at the time the earth formed. And of course, not only were the coal layers therefore formed at the same time during the flood, but these deep earth diamonds must have formed at the same time as the earth itself. And so we got a direct measurement of only thousands, not billions, for the age of the earth. Well, we can conclude that because these uncalibrated radiocarbon ages confirm the biblical time scale for a young earth in the recent flood, then the conventional ages of millions and billions of years derive from the long ages of decay of the uranium and the potassium and the rubidium, etc., must have been grossly accelerated if the radiocarbon has given us a closer estimate compared to the biblical timescale. So again, we have a 5th line of evidence of accelerated nuclear decay during the flood. Well, finally, let's turn all this from being our foe to being our friend. We've shown that there's problems with these dating methods, but if radioactive decay was grossly accelerated during the flood, then the radioactive ages, though inflated, should still yield relative ages in the correct order. What do I mean by that? Well, think about a volcanic rock layer that formed in the first month of the flood. It would go through much more accelerated nuclear decay than a rock layer that was formed in the last month of the flood, wouldn't it? The one at the bottom would have 12 months worth of accelerated nuclear decay, so it should give an older age, and the one at the top should only have a month's worth of accelerated nuclear decay, so it would only give a younger age. See? We can turn it from being an enemy to being a friend, to give us, so that means we can go from the known to the unknown and use this method to help us to understand the relative order during the flood, for example. Many of the accepted radioisotope ages, as I said, do match the relative order of the strata and their relative ages. So when we can't figure it out, the age of some rock layers from their immediate environments, it may be possible to use the radioactivity in the rocks as a guide to the relative age of these rock layers within the flood, whether it was early flood, middle flood or late flood. So we can still harness this method to our advantage. If we knew what the acceleration factors were, we could, in fact, try to correct these ages to give the correct ages from a biblical timescale. What continuing research is happening? Well, I'm planning to collect more granite samples to look at zircons for helium diffusion. I also have a meteorite and other rock units that I'm going to look at the four methods on the same rock or meteorite to see if we get continuing disagreement between the results. And radio halo studies are continuing on a variety of rocks, and you'll hear more about that on Thursday night, including rocks associated with mineral and ore deposits. What about radiocarbon? Remember, radiocarbon production is controlled by the cosmic ray influx, which is in turn controlled by the Earth's magnetic field. If the Earth's magnetic field was twice as strong as it was in the 1400 years ago in the past, twice as strong as it is now, which other evidence indicates it was, that means the radiocarbon production waste was half of what it is today, back then. And that means if we go to the flood 4,300 years ago or so, the radiocarbon production rate was very, very much less than what it is today. And also we had all that carbon from all the plants and animals in the pre-flood world that swamped the radiocarbon that we find in the fossils, and so it would only make for a trivial amount of radiocarbon in the fossils, and that's what we find, trivial amounts that give apparent old ages. So if we try to do some calculations, the huge volume of carbon buried during the flood was probably 100 times the amount of carbon we have in the present day biosphere. So that would have grossly diluted the normal carbon. Yet the conventional ages, these conventional radiocarbons, all assume the radiocarbon production rate today. So if we correct these radiocarbon ages on the basis of slower, smaller amounts of radiocarbon production in the past, we can correct these numbers. And in fact, if we do that, the 50,000 years ages for the coal beds during the flood, we can shrink that down to less than 5,000 years by just dropping the assumption that using the present rate of radiocarbon production rate and the swamping of the radiocarbon with a lot more carbon during the flood. So if we can devise a recalibration factor, then we can use radiocarbon to more accurately determine ages of rocks and archaeological artefacts to match the biblical timescale, and it would become our friend and ally. So more research is currently being done on radiocarbon, including samples directly related to the biblical chronology. Well, conclusions, and we quickly wrap up here. 1, the 3 assumptions which all radioactive dating is based are not provable because the past cannot be observed and measured and tested, and therefore these assumptions are not even reasonable. The resultant millions of years ages, though unreliable and highly inflated compared to the 6,000-year biblical time frame, usually still match the relative order of the rock units being dated. In the rate research, we uncovered 5 independent lines of evidence that demonstrate that radioactive decay rates must have been grossly accelerated during one or more recent catastrophic events, especially during the flood. Therefore, the radiometric dating methods cannot be trusted to date rocks and fossils at millions of years old. However, these methods may often be used as a guide to relative ages of rock layers. And the measurable amounts of radiocarbon in fossils and deep earth diamonds is consistent with the young Earth and the recent Genesis flood. Continuing research, therefore, can help us uncover the factors that we can use for corrections so that we can transform these grossly inflated millions of years ages into the timescale of the biblical account, and therefore turn these methods from being our foe to being our friend. Well, you've been very patient. Thank you very much. That was a lot to get through.